So we saw how to solve the free oscillation problem, which is the solution of the homogeneous differential equation d squared y dt squared plus c over m dy dt plus k over my. Remember that c and k are the constants telling us about the fluid and the spring, and m is the mass at the end of the spring. So if we keep the entire equation the same, but we make it non-homogeneous, what that's telling us is that there's some other acceleration in the system. It could be that the entire system is sitting on a rocking boat. It's moving up and down, and so that's going to impart an acceleration to everything. It could be that we have a little rocket engine that we put on the mass at the end of the spring, and we fire that off periodically. Maybe someone just comes up and gives it a slap. That extra term is called the forcing term. Again, though, this is just a constant coefficient linear equation, so we know exactly how to solve it. Because this is a non-homogeneous problem, the methods that we have depend on the form of what that forcing term looks like. So what we're going to do is assume that it's periodic forcing. So imagine that on the end of that thing there's a rocket, and we're just throttling it up and down periodically over time, where F naught is going to be the amplitude of the forcing, how much we're forcing it, and omega controls the frequency with which we're forcing it. So let's break this down into cases like we did before. The first case, which we didn't talk that much about in the homogeneous case, is the case of no damping. And that just means C is equal to 0. You can understand no damping as a kind of underdamping. So the first step we have to do is to solve the homogeneous problem. And again, we're going to, instead of carrying on the k and the m all the time, we'll just rename root k over m to be mu. So that homogeneous problem has a nice oscillatory solution. Then we need to find a particular solution. I won't go through the derivation of it, but you can do it if you want to. The particular solution that we get, if we use, say, the method of undetermined coefficients, is a multiple of cosine omega t. You can see that the thing that's going to control what multiple we have there is the difference between mu, which is to say the frequency that you get from solving the homogeneous problem, and omega, which is the frequency that you get from the forcing term. Let's go ahead and see what that looks like. All right, so here is a graph of the solution in the case with no damping. You can see that we've got a couple of different kinds of periodic behavior going on, and I want to explore that a little bit. In this case, mu, which is the frequency of the homogeneous system, is 3.03, and omega is 2.5. So here we've got the homogeneous system oscillating more frequently or faster than the forcing term. Let's see what happens as we sort of play around with that. Let's slow the forcing term down and see what happens. You see, as you take the forcing term down, you don't see it so much. You really see this 3.03, the mu period, is the distance between these peaks. You can sort of see it's like an oscillation stacked on top of an oscillation, and in fact, that's exactly what it is. Let's zoom out a little bit, so we can really see that. So it sort of looks like it's just wobbling, right? You've got this very low frequency oscillation, 0.9 is omega, and then on top of that, you've got the spring bouncing up and down. Okay, so let's see what happens as we increase the frequency of the forcing term. And you notice once we get that forcing term to be greater than the frequency of the homogeneous system, it sort of changes, right? Something really interesting changes. We get now the smaller oscillation that we see, the distance between, say, these two peaks, that's omega. And the slower oscillation, in this case, they're still pretty close, so they're sort of fighting each other. Sort of interesting behavior comes up. If we go ahead and increase the forcing frequency even higher, what do you see? Well, now it starts to look more and more like we just have that 3.03 frequency, and the little bobbles coming from the forcing term don't change it too much. So there's one case that we left out, and that's what happens if these two frequencies are the same. So if we happen to be forcing the oscillator at its natural frequency, or the frequency that the homogeneous system would have had were we not forcing it at all. Here's a solution in that case, and I just want to make the point that, first of all, there is a period here, right? It looks really nice, but also let's zoom out a little bit and see what's going on. You can see that if we do our forcing with the same frequency as the system wants to have anyway, roughly speaking, when it gets to the end, when it gets to the peak over here, well, we're forcing it some more. So the next peak is going to be higher and higher and higher after that. This is called resonance. Okay, and if you have a resonant oscillator, bad stuff can happen. That thing is just fluctuating more and more wildly. In the case of damping, again, we have three kinds of damping. There's underdamping, overdamping, and the critical damping. But in any case, if you use the method of undetermined coefficients or trying a complex valued trial solution, you'll get the following particular solution. Okay, so there's a lot of stuff going on there, but the thing to notice is just that it's oscillatory with frequency given by omega, which is the frequency of the forcing term. Okay, we've solved the homogeneous equation in each of the underdamping, overdamping, and critical damping cases, so now we can just plug that in. And the point is, each of these looks like an exponentially decaying term plus y sub p. So what does that tell us about our overall spring system? It says that if we ignore the exponentially decaying term, for example by waiting long enough that that term is negligible, the only thing we really see is the forcing term, which sort of makes sense. So initially, your spring is sort of moving in an interesting way, but it chills out pretty quickly, exponentially fast. It chills out down to just whatever the frequency of the forcing term was.